Hello and welcome to our second recitation video for week 2, where we discuss metric spaces in practice. If you haven't seen the first video, then I encourage you to go watch that now. That is the video titled Introduction to Metric Spaces. So in topological data analysis, data is often provided to us in the form of a point cloud, which is a finite set of points x. But to use many tools from topological data analysis, we need the input to be a metric space. So we have to convert this point cloud into a metric space. So how do we do this? Well, one of the most common ways is to view X as a subset of some ambient larger metric space and restrict the ambient metric function to X. A common example is if X is a set of points in n-dimensional Euclidean space, and dp is the Minkowski metric that was discussed in the previous video, then we take the metric function on x, dx, to be the restriction of dp to x cross x. Let's go through an example. So let x be the simple three-point space consisting of points x1, x2, x3, a subset of the plane r squared, with x1 equal to 1, 1, x2 equal to 1, 4, and x3 equal to 5, 1. If we define dx to be the restriction of the 2 Minkowski distance, also known as the Euclidean distance, to x cross x, then very easily we get that the distance from x1 to x2 is 3, the distance from x1 to x3 is 4, and the distance from x2 to x3 is 5. If we define dx to be the restriction of the 1 Minkowski distance, then we get that the distance from x1 to x2 is still 3, distance from x1 to x3 is still 4, but now the distance between x2 to x3 is 7. And lastly, if we define dx to be the restriction of the infinity Minkowski distance to x cross x, then we get that the distance between x1 and x2 is 3, the distance between x1 and x3 is 4, and now the distance between x2 and x3 is 4 as well. If x comma dx is a metric space with n points, then we can enumerate the points x1 through xn, as was done in the previous example, and the information of the metric function dx can be encoded in a distance matrix. So a distance matrix, capital D, is an n by n matrix where the entry in the ith row and the jth column is defined to be the distance in x between the point xi and xj. For the previous examples from the previous slides, we have the following distance matrices. So D1, the restriction of R2 to the set x when using the 1 Minkowski distance, we give the following distance matrix. When using the 2 Minkowski distance, we give the following distance matrix. And lastly, when using the infinity Minkowski distance, we would get the distance matrix d infinity on the right. So this is how metrics are really represented in practice, in computation. Whenever we are using actual software in TDA, a metric is encoded as a distance matrix in this way. One other common type of input in topological data analysis, which we'll discuss today, is a graph or a weighted graph. This is of particular relevance to our course because a lot of data from neuroscience is input in the form of a graph. And we'll discuss more on that in a moment. So let's give the definition. A weighted graph, denoted by G, consists of V, a set of vertices, E, a set of edges, where E is a subset of the vertex set cross itself. So every element of E, which we will call an edge, is just a pair of vertices. And lastly, weights, which is a function w from the edges to the positive reals, where we simply assign a number for every edge that we call the weight of that edge. So for an example, we have the following weighted graph. So it has 5 vertices, v1, v2, v3, v4, and v5. It has 6 edges, and we represent the weights by the integer which is plotted along an edge. So for instance, the weight of the edge v1, v2 is equal to 3. So going back to real-world data, in neuroscience, the brain is often modeled as a collection of vertices where each vertex corresponds to some region of the brain. Then an edge is connected between 2 vertices if the 2 regions of the brain corresponding to the vertices interact in some way. And sometimes we get this in form of a weighted graph where the weight represents the strength of the interaction, such as the amount of information, the number of signals being sent between these 2 regions of the brain as one example, and we'll discuss that in more precision and more detail later on in the semester. So a weighted graph, this is nice, but we do still want to convert this to a metric space in many cases. So how can we do that? Well, first, let's give the definition of a path. A path P between vertices u and v, which we'll denote by P from u to v, consists of a sequence of vertices v0 through vn, where v0 equals u and vn equals v, such that for all I between 0 and n minus 1, vi, comma vi plus 1 is an edge. So for instance, if we wanted a path from v1 to v3 in this example, then v1, comma v2, comma v3 would be a path. v1, comma v4, comma v3 would also be a path. And v1, comma v5, comma v4, comma v3 would also be a path from v1 to v3. Now we define the cost of a path. So the cost of a path P is this function, which we denote by C, where C of P is defined to be the sum from I equals 0 to n minus 1 of the weights of the edge from vi to vi plus 1, where these are vertices from the path. If G is an unweighted graph, so that's simply a weighted graph where we forget the weight function w without that information, we can still view it as a weighted graph, and the standard approach to do so is to set the weight of every edge in the graph equal to 1. Now we define a function dv from v cross v to the reals by setting dv of uv, u comma v for any 2 vertices u and v in the graph, to be the infimum over all possible paths from u to v of the cost of p. Now, for vertex v, v comma v may not be an edge. There may not be an edge from a vertex to itself. But by convention, we assume that there is always a singleton path from a vertex to itself with the cost of such a singleton path defined to be equal to 0. Using this convention, we can show that v comma dv, as defined above, is a metric space. And this dv is often called the shortest path distance. It is also sometimes referred to as the geodesic distance in the graph. So let's go back to the example we considered a moment ago. So here we have a weighted graph. Using the definitions on the previous page, let's compute the distance matrix capital D. So let's just go through one quick example. Suppose we wanted to find the distance between v1 and v3. Well, we listed 3 paths earlier, so we know there's a path going from V1 to V2 to V3. The cost of that path is 5, which is the sum of the weights of the two edges on that path. I also said there is a path going from V1 to V4 to V3, which similarly has cost 5. And there's also a path from V1 to V5 to V4 to V3. And even though the number of vertices in that path is larger than the previous 2 paths, the cost of that path is less because the sum of the weights along the edges is only equal to 4. And you can check all possible paths and see that the distance from V1 to V3 is realized by this path and is equal to 4. I encourage you to pause the video for a moment and just compute out the remainder of this distance matrix D. Okay, so maybe you've computed out the distance matrix, and here is what it looks like. And for example, the distance from V1 to V3 we just found is 4. Again, in distance matrix, that's going to correspond to the entry in the first row and third column being equal to 4, which is as we see here. So now let's move to MATLAB and see how we can implement some of the topics discussed in this video in MATLAB. Okay, so here we are in MATLAB. Now let's go through some examples. So the first example will be the first example from earlier in the video with a simple 3-point metric space and a triangle in the form of a triangle on the plane. So to define the point cloud, we define the x-coordinates of the points, the corresponding y-coordinates of the points, and then the point cloud as the n×2 matrix with the first column representing the x-coordinates and second column representing the y-coordinates. Next, I use the scatter function to plot these points. Now the important part is the distance computation. So the key function is this pdist function, which is a built-in function in MATLAB. The inputs to this function are the point cloud x, as described above, and then you tell the function what distance to use to compute the distance matrix. There are a wide variety of different metrics that are built in and available to use in the pdist function. I encourage you to look through the documentation to see what all the options are. Here, we're telling pdist to use the Minkowski metric with p equals 1. Then, as we'll see in a moment, the pdist function does not output a distance matrix in the square n×n matrix form that we're used to. If we want to convert the output of pdist to look like this, we just use the square form function. So we'll have the code, the function pdist, do our distance matrix computation for Minkowski distances with p equals 1, p equals 2, and p equals infinity. So let's run this code. So first, we see the pop-up is just the plot, demonstrating that this is in fact the metric space we started with at the beginning of the video. And now let's look at the outputs. So first, as we said, x the point cloud, n×2 matrix, first column x coordinates, second column y coordinates. Now the output of pdist is just the 1×3 vector with entries 3, 4, and 7. When we convert it to a square distance matrix, you note that it's the same as the square distance matrix we computed earlier, excuse me. But the 1×3 vector of distances that pdist computed is actually equivalent in terms of the amount of information to this 3×3 distance matrix. Because note that these 3 distances are the 3 non-zero elements. So what's going on here is pdist computes the distances and gets rid of and doesn't deal with the redundant information of the zeros along the diagonal or the symmetry between below the diagonal and above the diagonal. So for computation purposes as well as memory storage, the output of a pdist function is often what we're going to be inputting as a quote-unquote distance matrix. And then we had it print the two other square distance matrices, which you can go back and check, agree with what we computed earlier. So now let's go to a larger example. So here we are going to be generating 100 random points with coordinates, both x and y coordinates, between 0 and 1. As before, I'll simply plot the point cloud, and then we will again have MATLAB compute the Minkowski distances with p equals 1, p equals 2, and p equals infinity. So let's run this code. And we see it was basically instantaneous. In fact, the majority of the runtime here is coming from printing the 100 by 100 distance matrices in the command window. So here we simply see the 100 random points that were generated with x coordinates and y coordinates, all between 0 and 1. And then in the command window is output the distance matrices. And here you can look at 99th through 100th columns. And we saw, again, that this was not instantaneous. Now, in practice, we generally will be working with point clouds for which there are far more than 100 points. So let's try changing this so that there are now 10,000 random points. We run the code, and we see we have to wait for a couple seconds, but after just a few seconds, maybe 3 or so, there's the plot of the now 10,000 points in this square in the plane, and I didn't have MATLAB print the distance matrices due to their size, but we can verify that these 3 distance matrices are stored in memory, and they are 10,000 by 10,000 matrices as expected, and MATLAB was able to compute all 3 of them in just a matter of a few seconds. So this is very, very fast and shows that the built-in functions for distance computation from a point cloud in Euclidean space with the pdist function is easily able to handle on the order of magnitude of tens of thousands of points, and if you're willing to let it run for a little bit, can certainly handle hundreds of thousands of points as well. Now, let's go to our last example, where we discuss graphs and converting weighted graphs into metric spaces. So here, we define a graph in MATLAB. So graphs are a built-in type of object in MATLAB, and this is how you define them. So what's going on here? Well, you start with one list which contains node labels. So here, this means node labeled 1, node labeled 1, node labeled 2, node labeled 3, and 4. The second list is also a list of node labels, so node label 2, 4, 5, 3, 4, 5. And the ith element in the first list and the ith element in the second list have an edge between them. So this means the node with label 1 has an edge connected to the node with label 2. Similarly, the node with label 1 has an edge connected to the node with label 5, and the node with label 4 has an edge connected to the node with label 5, and so on and so forth. Next, we can define weights as, again, a list with the same length as both of the 2 lists in our graph definition. And each number here corresponds to a weight of the corresponding edge in our graph definition. So here, the weight 3 is assigned to the first edge in our graph, which is the edge connecting vertices 1 and 2. Similarly, we assign weight 4 to the second edge, which connects the vertices 1 and 4, and so on and so forth. Then we plot this graph. MATLAB is able to plot graphs as built-in, and we label each node V1 through V5 just so it agrees with our picture earlier. Then MATLAB can compute shortest paths as well as the distance matrix using the shortest path distance. So let's run the code and see what we get. So here we see the same figure that we saw earlier with the vertices, edges, and edge weights. Now, let's look at the output. So here we just had MATLAB return the edges, and you can see the end nodes of each edge and the corresponding weight of that edge. And you can check that this agrees with our figure on the right. Then the shortest path, we asked MATLAB to compute the shortest path between vertices 1 and 3. As we discussed earlier, this shortest path goes from V1 to V5 to V4 to V3, which MATLAB computed for us. And then the distance matrix, using the shortest path distance, MATLAB computed as D down here. And you can go back and check with earlier in the video that this agrees with the distance matrix we computed then. So these are just a few common approaches for ways to compute metric spaces from point clouds and graphs in practice, and how to do these tasks from a computer science perspective in MATLAB. Thank you.